Hello again. In this video I will examine two algebraic numbers and their corresponding extensions of rational numbers. The first number will be the square root of 2. Before we proceed building the corresponding field, let's make sure that this is not a rational number. Otherwise, attaching it to rational numbers will just give us back rational numbers. So that verification, that fact that this is not a rational number goes back to ancient times, to at least ancient Greece. Let's assume that it is a rational number, so it has a form of p and of a q, with p and q being integers. We can rewrite this equation as twice the square of q being the same as p squared. And if we look at it, and if we remember that any integer is uniquely factorized into the product of primes, we will have a contradiction, because counting how many 2's we have in the factorization of the left and of the right, we will have a mismatch. On the left, the number of 2's will inevitably be odd, and on the left, the number of 2's will have to be even. So this is impossible, and hence this is impossible, and we have our irrationality of the square root of 2. And the rational numbers can be of two sorts, can be algebraic or transcendental, and of course this one is algebraic because it is a root of a polynomial t squared minus 2. Just by the very definition, we define this number to be the positive root of this polynomial. And moreover, this polynomial is irreducible over the rationals. Because if it is not, it has to be a product of two linear terms, and linear terms will have to be t minus some rational number, and these rational numbers will have to be square root of 2 and negative square root of 2, and we know that they are not rational numbers, so the factorization we seek is impossible. So again, alpha, our square root of 2 is the root of this, and hence it is algebraic. Remembering what was proved before about this field, we can describe it as a quotient of the polynomial ring by the ideal generated by this irreducible polynomial. Such a reducible polynomial, an irreducible polynomial which has given alpha as its root, is unique if it is monic, and it is called the minimal polynomial of that number alpha. So we have this minimal polynomial here, we construct this quotient ring, it has to be a field, and moreover, evaluating on alpha on the square root of 2, any polynomial evaluating on alpha will give us a homomorphism, but this homomorphism will be an isomorphism if we quotient by its kernel. So this is a nice algebraic ring theoretic description of the field we are trying to construct. Looking at this side, we can remember what we can say about congruence classes, modular and polynomial. They are remainders of division by this polynomial, and we can be sure that any remainder will have to be linear because we divide it by something quadratic. So any linear polynomial can be decomposed into some number of 1's and some number of t's. As a vector space, differently saying, as a vector space over Q, our quotient is spanned by two vectors, the class of 1 and the class of t. Let's translate this information to the other side and describe this field we're constructing as a vector space. And the translation is evaluation at the square root of 2. So we just need to evaluate our basic vectors, and we will get basic vectors in the field we're constructing, and they will be 1 and square root 2. So again, the statement is that any element in here can be described as a linear combination of 1 and the square root of 2. Hence, we have a very explicit description of numbers in this field. They are linear combinations with rational coefficients. Now the statement that this is a field is a statement about arithmetic of those numbers. The sum of those numbers is of the same shape as the numbers, a linear combination of 1 and the square root 2, the product, the difference, and the inverse. So let's look at the inverse. And the inverse is most interesting fact. what it says is that the inverse to this number can be written as some combination of a and b put in the numerator and the denominator plus or minus some combination again of a and b times the square root 2. So this is going to be a rational number, this is going to be a rational number, moreover it is going to be a polynomial expression, or a rational expression, polynomial of a polynomial in a and b, and the same in here. So let's find those terms, and the trick is to use the difference of squares, so to multiply by what is called the algebraic conjugate of this number, which is just the number with a flipped sign in front of the square root 2. And then the difference of squares formula will give us a squared minus b squared twice. So we can see that this is a rational number always, and this is never 0 unless a and b are both 0. The proof of that fact goes exactly the same way as a rationality of the square root 2. And then we can take this number and divide by this rational number, because it is not 0, and divide it into a and into b, and we'll have our rational coefficients, we'll have our neat expressions, polynomial expressions for the coefficients of the inverse. And that is a formula which works for all non-zero numbers in our field, give us inverses, manifesting the fact that this is a field. So now let me look at the second number, the second example. The number will be a primitive root of degree 3 of 1 computed in complex numbers. So this is a compact Euler notation for it, which is abbreviation of this complex number notation. It is a cos function of 2 pi over 3 computing the real part, and the imaginary part is computed by the sine function of the same argument, 2 pi over 3. And we can write it even better in algebraic form by looking at what cos and sine will have to be. So the negative 1 plus I square root 3 all over 2. This is a number which is a root of degree 3 of 1. So it is an algebraic number, it is a root of a polynomial. So when we attach it to the field of rationals, we will have some proper extension, because this is not a rational number, obviously it is not even real. And the polynomial we will need for analysis, like in here, will have to be this minimal polynomial for this number. So it has to be a polynomial for which epsilon is a root, and it has to be an irreducible. If we take this polynomial equation, which obviously vanishes on epsilon, and look at it as a polynomial, it's not irreducible over the rationals, because we can factorize it into 2 t minus 1 and t squared plus t plus 1. And obviously epsilon is not a root of this, epsilon is not 1. So epsilon must be a root of this. And this is going to be its minimal polynomial, because by the previous argument it is of degree 2, so if it factorizes at all, it has to factorize into linear terms. It has to have roots in rational numbers, but one of the roots we know it's epsilon, and the other it's epsilon conjugate. So they are not rational, hence this is irreducible over the field of rationals. And as before, we can construct an isomorphism of the field generated by epsilon and the quotient of the polynomial ring by the ideal generated by this irreducible polynomial. So the same evaluation, the same type of homomorphism evaluation on epsilon now will give us this identification as fields. As a vector space, this is spanned by 1 and t still, the same argument, this is quadratic, so any remainder will have to be linear. Translated onto this side, we will have the Spanian statement as follows. This, as a vector space over the rational numbers, is generated by 2 of its elements, 1 and epsilon. So now we can, as before, write explicitly all the elements in this field as linear combinations of 1 and epsilon with rational coefficients. And as before, we should be able to write the formula for the inverse. All other formulas are more or less straightforward, but the formula for the inverse is the most interesting. Again, it should be consisting of two rational expressions of a and b computing the coefficient for 1 and the coefficient for epsilon. What are they? That's a question, my question to you. It's not that innocent. If you try to use the same trick, you won't succeed. Trying to bring it to the difference of squares will not cut the mustard. If you compute the difference of squares, it will not be rational. If you just flip the sign and make the formula for the difference of squares, it will not be giving you a rational number, so you will not be able to bring it into the denominator and get the answers here. So something else is required. Please think about it. Bye for now.